Hey there, and welcome back to How'd You Get That? Today we are tackling this problem involving combining functions. Can you describe the behavior of this function? F of x is equal to x squared over sine x in that it behaves both as a quadratic function and as a sinusoidal function, or trig function. Notice that I can rewrite this function as f of x is equal to x squared times the cosecant of x. This doesn't change the function at all, but it might give us some insight into how this function behaves. For instance, we know that the cosecant has vertical asymptotes at multiples of pi. So at negative pi, 0, pi, 2 pi, 3 pi, 4 pi, etc. And we might expect this function to have vertical asymptotes in similar places. We also know that the cosecant oscillates between negative infinity to negative 1 and from infinity down to positive 1. So we might expect it to have similar behavior there as well, or at least behavior that oscillates or repeats between certain values. Let's take a look at what happens when x is equal to 0. We know that the cosecant function is undefined at x is equal to 0, but the quadratic function, that goes to 0 when x is equal to 0. So we have this indeterminate form, 0 times negative infinity, or really positive infinity here, because the cosecant actually diverges at that point in terms of its end behavior at the line x is equal to 0. So what's going on here? Well, it turns out that the function wants to approach 0 at this point, but it never actually hits 0. There's actually a hole at x is equal to 0. If we zoom way in, we can see that this function converges almost to 0, but then actually doesn't have a value at x is equal to 0, as we might expect. But at the same time, it doesn't have a vertical asymptote at x is equal to 0. Okay, so we've observed what happens at x is equal to 0, and we found all those vertical asymptotes, but are there, for instance, any x-intercepts? Well, that would be where the whole function is equal to 0. But unfortunately, where the quadratic part goes to 0, the cosecant part is undefined. So there's no x-intercept for this function. Now let's take a look at what happens when the cosecant part oscillates between the values of 1 and negative 1. Well, at those points where x is equal to pi over 2, or 3 pi over 2, or 5 pi over 2, etc., we have values of 1 and negative 1, which means that the whole function, the whole combined function, goes to either x squared times 1 or x squared times negative 1. So we get a series of points along the function here that are exactly equal to what the function would be if it was just x squared, or negative x squared. So we can actually superimpose either of those functions onto this combined function, and we can see that the quadratic function x squared or negative x squared is actually tangent to certain points along this combined function. And if we zoom way out, we can see more of this pattern emerge. In fact, this whole function is enveloped by the two functions x squared and negative x squared. But it also has the oscillating behavior with vertical asymptotes of the cosecant function. So on the greatest scales, this function kind of looks like a quadratic, but on the more up close and personal scales, it kind of looks like the cosecant function. Now, if we investigate the end behavior here, we would expect the end behavior to be undefined because cosecant doesn't have a defined end behavior, whereas the x squared function does. But because one of them is undefined, both of them together must also be undefined. However, if I look at just the y values greater than 0, then I can see that the end behavior looks very much like the x squared function. And if I look at y values below y is equal to 0, then I can see that the end behavior looks like a negative x squared function. Looking at the domain and range of this function, if I look at the domain is restricted to the same domain as the cosecant function. And that's because the cosecant function is restrictive of its own domain, which is from all real numbers x not equal to multiples of pi. The quadratic function doesn't have any restriction on its domain. It's all real numbers. So the restriction of the domain simply falls on the cosecant part of the function. The range of this function is all real numbers except for y is equal to 0. we can see that the cosecant function converges closer and closer to 0 as the x squared part of the function also reaches x is equal to 0. We're getting to smaller and smaller values, closer and closer to 0 as we reach x is equal to 0. However, we know that this function is undefined at x is equal to 0, where the function would have had a value of y is equal to 0 if it were simply just the x squared function. But we can see that unlike the quadratic function, which would only be defined for y is greater than or equal to 0, this function is actually defined for all values negative infinity up to 0, non-inclusive, and 0, non-inclusive, to positive infinity. This is because of the nature of the cosecant function, where since it has negative values, the quadratic function will take on those negative values as it's being multiplied by the cosecant function. That's why we have a functional envelope of either x squared or negative x squared for this function. So that's how this combined function, x squared over sine of x, has properties of both the quadratic function and the trigonometric function. If you have any questions, leave them in the comments below, along with any suggestions you might have for future episodes of How'd You Get That? Hit that like button, subscribe, and hit that notification bell so you never miss another math, physics, or problem-solving tutorial. Thanks so much for watching, and I'll see you in the next problem.